Okay. I want to change our type of distribution, but we're going to continue in the same vein as we did yesterday, Monday. Today is Wednesday. So now let's think about the difference between discrete and continuous. We did this when we were talking about data types. We had nominal data, we had discrete numerical, we had continuous numerical. What was the difference between discrete and continuous?
Like between any 2 points, it could be a lot of things.
Aha. And discrete meant, right, it's finite sets of outcomes. So here, so I count my outcomes there, the first one, the second one, the third one, however many there are. Like when we were doing the ages ranged from 20 to 60, there were 41 possibilities. But in a continuous setup, we have an interval. So if I said from 20 to 40, I'd be thinking of the whole smeared out number line between 20 and 40. And instead of being separate possible behaviors, I now have a real number. For example, if instead of treating height as exactly measured in inches, then I'd be able to say, oh, you are 5'11" you are 71 inches tall, you are 6'3", you are 75 inches tall. I could take that much finer, right? I could go to quarters of an inch, I could go to hundredths of an inch, I could do it in centimeters, millimeters. I could measure your height depending on how puffy your hair is that day, right? Well, maybe. But the whole idea is that I can cut that finer and finer and finer. And that makes the difference here between an integer and a real number. And these are usually measured items. Height, weight, we can categorize them, but we tend to think of them more in continuous terms. But now I have a problem. I'm going to make up a couple of numbers moment. Let me just suppose that A is 0 and B is 10. And I say I'm going to pick a number randomly between 0 and 10. I would like each of you to pick a number between 0 and 10. What's the chance you picked my number? You don't even know what my number is, right? Give me a number between 0 and 10. Okay. Give me a number. 2, 4.
7, 3.
Problem. I picked my favorite number. I picked pi. 3.14. What's the chance you're going to pick my number? It's 0. There's absolutely no way you and I are going to get the same number all the way down all the infinite number of decimal places, right? So here's the problem in that the probability of X equals a particular value is very, 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 very small. It's so small, we say it's 0 when x is continuous. So it makes much more sense, instead of looking at the chance that x is equal to a number, to look at the chance that x is between numbers. Like if I had said, what's the chance your number is between 1 and 4, a bunch of you would have gotten that. Some of you would have picked numbers outside that range, right? But then I can say, I can figure out the chance of your number being in some section of my interval rather than picking the exact same spot. Problem. The actual math behind what we're going to do is calculus. We're not going to do the calculus. But there are two concepts from calculus I need the idea of. And the first is that my probability distribution is now a function. Wait a minute. Algebra class. This isn't even calculus. Algebra class. PDFs now are graphs of functions. I don't know what the graph looks like. I just made something up for the moment. But then I can say, I need to know about this function to make it a valid probability distribution. I still want my rules for a PDF to hold true. Rules for a PDF. Stuff we did a little over a week ago when we started chapter 6 told me I need to know two things. I need to know that this function, whatever it is, always spits out positive numbers. The probability of something has to be between 0 and 1. So these functions have to give me numbers between 0 and 1. And if I think of the chance between A and B, then I really want to say that that should be the area here, the area under my curve. Now this, I think, helps me understand why the probability of getting exactly a particular number, is 0. Because you have an area that starts here and ends here. How much area is under the graph right at this little spot? There's no area there. The left edge and the right edge are the same thing. I can't make an area. So that helps me justify this claim that each individual spot is a 0. We had one other comment about probabilities, and that was that if you added up all the probability, what did you get? 1. Which means the total area under this curve, from as far left as you want to go to as far right as you want to go, has to be 1. But technically, that would be an infinite area, infinitely far to the left and infinitely far to the right. And that means that as our curves go out in that direction, one of two things has to happen. They have to stop and be zero from some point on, or they have to get so small that they effectively contribute no area. In calculus, we use an integral. The area under a curve is the integral from A to B. Of whatever this function is. Now, this is almost going to be the last time. We might see this notation one other time, but I wanted you to see it here so that when somebody asks you, what are you really doing? This is the calculus piece. You're figuring out areas under curves. But I think more than important than this idea is that picture at the top of the screen that shows this as an area under a curve, because I think it's going to be a lot more important for us to remember that picture. Now, that means as long as I can draw a curve and I can figure out the area under the curve, and my curve obeys the two rules we have for our probability ideas, that the function is always positive and the total area is 1, I've got a valid working PDF. So, a picture like this one. We've seen this picture before. That's our normal distribution. Notice over there on the right-hand side, we're looking at a distribution of speed in miles per hour. And the probability that somebody is going a given speed on this stretch of highway is given by the chance over there on the left. These don't get very big, right? That's about an 8% chance of somebody doing around 75 on this road. I can spread that out and I can measure an area under this curve. And I can get, say, what's the chance of somebody going between 70 and 80 on this road? I could measure this area under the graph. What's the chance somebody's going faster than 85? I could measure this area under the graph. What's the chance somebody's going slower than 60? That's really, really small, isn't it? But I could find out a way to measure the area under this graph. This is the cumulative distribution function. Notice this goes from 0 to 100%. And that shows you the total area from all the way on the left to some point. This is going to be really useful, this cumulative distribution function. But then I'm thinking of areas. Those pictures are on page 234. So I have a probability function, and I want to know if this function is going to work. So here's a function. This is a piecewise defined function. It's defined in two different pieces on two different sections of the x-axis. It's 0 everywhere except between 0 and 1. I'd like you to draw me a graph for this function. What's this graph look like?
box from 0 to 1
And the height of that box is 0.25. Absolutely. So my question to you is this a valid PDF? It's a function. Can I use it as a probability? It needs to obey two rules. Are the values ever negative? The values are either 0 or a quarter. The values are always non-negative. That's good. Is the total area in that box 1? Geometry question, what's the formula for the area of a box? Length times width. What's my total? Because it's only 1 unit wide and it's 0.25 tall, the total area is 0.25. This is not a valid PDF. Length times height in our case, right? Rather than width, height of the box. That's not a good function to be a PDF for something. There are two different ways I could fix this, because if we think about it, this kind of reminds me of our uniform distribution. It's the same output everywhere we've defined it, right? It's uniformly high between 0 and 1. So this kind of looks like my uniform idea. There are two different ways I could fix this. How could I make the area of the box equal to 1?
Either make it higher or longer.
Exactly. Either make it longer or make it taller. So if I changed this function, then the area in the box would be 1, right? Because now it's 4 units long and 0.25 high. I multiply that, I get 1. That works. Okay. Now, again, the picture of this PDF is a horizontal line segment. It's a box. But I don't have to have a box. Draw me this graph. And let's see if we can answer the same question. Is this function a PDF? What's this graph look like? Max?
I'm trying.
Because that's a line, y equals 2x, a line with slope 2. If you have a graphing calculator, you can type that exactly in as y equals 2x. But then we only want the part of it between 0, 0, and 1. Huh, okay. Okay. Again, I asked the two questions. Is this function ever negative? The values it spits out are either 0 or they're on that line. That's always non-negative. Total area. Formula for the area of a triangle. Length times width divided by 2. So length times height divided by 2 equals 1. Yay, it worked. Now, the worst part about this course is that any function that satisfies these two rules could be a PDF. And that gives me infinitely many choices to play with, and that's going to suck. And I would then have to figure out areas under those curves. That's what I do in a calculus course. I'm not going to do that here, which means I am going to cheat. And I'm going to restrict myself to a small number of choices. I'm going to use the same two we used last week, Monday and Friday previous. I'm going to do the uniform and the normal. So let's talk about the uniform distribution. Well, this is going to look like a horizontal line, just like we were looking at in the previous picture before this. I just need to make sure that the length and the height match to give me 1 as a total area. So let me think about this from a picture standpoint. My function should be 0 outside of this section from A to B. And it should be some height here. How long is the bottom of that rectangle? How far is it from there to there? That's exactly right. And if I want the total area to be 1, then this number times the height should be 1. And that means that the height should be 1 over that number. Well, now I can actually write the function itself. And it's a piecewise function, just like our triangle was, just like our previous setup was. We're going to call this UAB, the uniform distribution function from A to B. And it's of X. That's the notation used in the textbook. Otherwise, I wouldn't write it down. Just remember uniform, it's flat. I just have to know from where to where. It turns out that it is fairly easy to figure out the CDF here. It's actually directly computable. This is the PDF. The CDF looks like a triangle. And what's more, I can give you the equation for this line. Now, here's the fun part. Something I haven't mentioned yet. If this is a PDF, what did we do with our PDFs in the homework for chapter 6? We asked about their means. We asked about their standard deviations. And we had formulas for those standard deviations and means. I remember there was a formula for the mean. And there was a formula for the standard deviation as well, right? It was a big, messy, ugly calculation, but we could do the standard deviation from the variance. And I also went and said that, I don't like using these formulas all that much because the calculations are messy. And so for each distribution, we actually let the book give us these values. Turns out the exact same process works in calculus. This big integral symbol that we used, this notation back here, in calculus notation, that's the letter S. That means sum, just like this. So it turns out that the way we get a continuous mean and a continuous standard deviation is to use these same formulas, just the calculus versions of them. So I can actually come up with a mean for this distribution by doing calculus. Now, I'm the only person in the room who probably likes calculus. I think it's really cool, but I don't want us to do it. So I'm going to say that for each of our distributions, we will have given to us the calculations for standard deviation and mean. And for a uniform distribution,
Gee, that looks familiar.
it's the middle. of the box. Halfway between A and B, it's the average of the two numbers. That's exactly the same as it was in the discrete case. For the standard deviation, the only difference is that I don't add the 1. And the reason I don't add the 1 this time is because you can't count the actual edges. You can only count the area in the middle. Again, the assumption here is that it is a uniform distribution. You should only use this distribution if you think no probability is more or less likely than another in a continuous sense. All of these formulas appear, all of the numbers here, at the top of page 236. There's our PDF, our CDF, the average, and the standard deviation. And what's more, there's an Excel command. I can do this in Excel. I can make it generate the PDF for me. I won't do that often, but I can make Excel give me numbers in certain ranges. So let's put this to use. Problem number 9 says that the expected arrival time of a bus is 10:20 a.m. But after measuring for a good long while, we actually say that the actual arrival time is a uniform distributed random variable whose times range from 10:18 to 10:22. Oh, sorry, 10:23. I had to read the number correctly off the book. So if it turns out that this is the actual expectation after measuring a bunch of these buses, it's uniformly distributed, when should we get the bus to arrive? What's my true expected value? Say again? Right. That's 5 minutes. So half of that is 2 minutes and 30 seconds. 10:18 plus 2 minutes and 30 seconds. 10:18:00 is 10:20.5 or 10:20 and 30 seconds. What's a standard deviation in this case? I just pushed the formula off the top of the screen. Hopefully you wrote it down. Works for me. Square root of b minus a squared over 12. B minus a, that's the length. That's 5 minutes. 5 squared is 25. Divide by 12. And 1.443, you said? Minutes. Now, these are the defining characteristics of this uniform distribution. The average and the standard deviation. But let me ask a question. What's the chance the bus arrives on time or early? Now, let me turn that into a probability setup, the P of something. Let me write that as P of. What's the of? The chance this bus arrives on time or early.
Be less than 32, 10, 20.
Aha! My arrival time should be less than or equal to 10:20. Now, rather than do algebra, rather than grab a formula and try and figure out which formula it should be, I'm going to draw a picture. What's the picture of this PDF? Every uniform distribution, every one of them looks like this. I want this picture with our numbers. So what should the picture look like? Say again? It is just a box. And that box starts at? Say again? And ends at? 1023. So it's uniform from 1018 to 1023, and that means it's got a height. What's that height? Exactly. 1 over B minus A. Now, sorry, the piece I want, goes from 1018 to 1020, right? So the piece I want to answer this question should stop here. So now I can ask the question, what's the area I shaded in? Almost. It's length times height. But the length of that box is 2. 1020 to 1018, right? It's only 2 minutes wide, and it's 1/5 tall. So this is 2 minutes. 1020 minus 1018. So this is 2/5. I didn't need to do any math. I just needed to draw the picture and shade the piece of the box I wanted. What's the chance the bus is late? It's the rest of it. 1 minus the chance it was early. Oh, I like it. As much as I want to use the two formulas that we came up with, it's a horizontal line, so I'm just doing areas of boxes. I don't need the formula for that CDF. I really don't. All I need to be able to do is to draw this picture. Ladies and gentlemen, my favorite, absolute favorite part about this distribution is it's a box every freaking time. And as long as I can figure out how long the box is and how tall the box is, every question you can ask me about this distribution is measuring the area of a box. Questions? That's all well and good. We did the uniform distribution in discrete version. Now we have the uniform distribution in continuous version. So now I had the binomial distribution, my Bernoulli thing, where we didn't have a uniform behavior. We had that peak in the middle. We had the histogram that we did from our coin flip experiment. We had a bunch of different pictures that went with that distribution. The continuous version of the binomial is called the Gaussian or normal distribution. But that's exactly the bell curve we've already seen. Remember the one I was showing you about speeding on a particular highway? Chance between 60 and 90 miles an hour, or whatever that picture was. Every Gaussian distribution has as its picture a bell curve. Page 238. Now, there's something really important to notice about this picture on page 238. So let me blow it up a little so we can see that PDF better. Look at the x-axis. There are no numbers on the x-axis. What tells me about where this curve is and how wide it is versus how tall it is are the average and the standard deviation. So it turns out that in order to build a normal PDF, you need to know those numbers in advance. They're the parameters we use to define our PDF. Problem. The PDF itself has an absolutely disgusting formula. I am never, ever, ever going to use that formula. Not once. No, not just no, hell no, nope. The CDF cannot be written down using any nice notation other than it's the area under that thing. So as far as algebra goes, F it, I'm not doing this. But both the PDF and the CDF are available to us directly in Excel. I'm going to use this norm.dist, normal distribution function, a lot to do these calculations, to avoid having to do a crap ton of calculus. Because there's an easy way to approximate the area under a curve on a computer. And it means I don't have to do it manually. In addition, if you have a graphing calculator, all of these distributions live here too. Please notice right above this button that says variables, it says, well, it's kind of hard to read there. Let me turn off the little light. It says DISTR. That's distribution. And if I hit second and this key, I get a bunch of distributions. And the very first two are the normal PDF and the normal CDF. Much further down this list, by the way, see that little arrow? Means there are more down. The binomial is actually on here as well. As well as a bunch of stuff we didn't do. We didn't do the Poisson, we didn't do the geometric, we didn't do the chi-square at all. But these first five, we'll end up using a lot. Most of what we'll do at the moment are these first three. But so far, I've only talked about the first two. How do I make this work for me? I'm going to draw this picture over and over and over and over and shade in pieces of it. And then I'm going to ask the computer to figure out the area between here and here. I'm not going to do the math. I don't want to. You can't make me. And I'm certainly not going to make you. But make a photocopy of this. Take a picture, print this out. We're going to get used to shading this sucker in a bunch of different ways. Even if you draw a crappy picture is enough to tell me what calculation I then need to do. But those are the calculations we will start doing on Friday. So I will see you all then. I hope you have a wonderful rest of your day.